Okay, let's start our lecture today. Okay, and this is the last chapter in this semester, which is chapter 7, and we are talking about the issue of the functional form of regression equation. Okay, and again, we say linear regression. Linear means linear in the coefficient. Okay, linear in the coefficient. So, for example, equation 7.1, this is linear in the coefficient because the power of the coefficient is equal to 1. Okay, and look at this one. This is, the beta is not a coefficient. The position of the beta is the power of the x. So this is not linear in the coefficient. Okay? And we have several alternative functional form which is also linear in the coefficient. Okay, for example, and by the way, if we have different functional form, the explanation of the beta coefficient will be different. Okay, will be different. So let's sort of review how to interpret the beta coefficient if we have different functional form. Okay, first of all, if it is linear, okay, before I never talk about something like this one. Okay, this is something, we call it, it's the calculus, okay, which is the derivative, okay, of the regression function. So for example, this one, let me write it down. If I have the functional form like this one, beta k xk plus exponent. So this is called linear in the coefficient as well as linear in the variables. Okay, so each of the beta function, we call it slope. If it is, this is multiple regression. So in terms of interpret the meaning of any of the beta, so like we will say it is the derivative of the y with respect to some particular x. Okay, so mathematically we should say derivative of the y with respect to either one of the, this is derivative, okay? And this is k. So if I take the derivative of the y with respect to either of the x, then it turns out to be the beta 1 only, beta k only. And we interpret the beta, any of the beta, as when the measurement units of x increase by 1, then the y will increase or decrease by the beta k units. Okay? So this is the regular, so far we all talking about the regression form is linear, functional form is like this. Okay, but from now on, we are talking about several linear forms, okay, instead of just this one. And we call this one is a linear form. And the other one, which meets the requirements of linear in the coefficients, is other alternative forms, which we have that summary table in our textbook. Let me see, is table 7.1, okay? And So we talk about the first one is linear form. The second one is called double log form. Double log form is using the ln of the y with respective the every one of the x or either one of the x. Okay, so if I have this one, x1, let me just put it just 2 x variables. Okay, and this is beta 2. Okay, if it in this case it turned out to be this one, and we call this elasticity. This is called slope. This is called elasticity, and it is also the derivative of the log 1. So it means the derivative of the log y with derivative of the log x. Mathematically, this is equal to this. Okay? Then it turned out to be the beta, and there's something like this one. So this is just beta, right? And this is beta times something like this one. Okay, so which is different? If you don't really understand this one, really, it doesn't matter. Since we have the different terms, one is called slope, the other one is called elasticity, then the meaning of that must be different. Okay? So we say the slope is the one measurement increase in x will have beta k measurement units increase or decrease of the y. But how about this one? This one we call it elasticity, and this is the percentage change. This one is called percentage change, right? This one is also called percentage change. So the meaning of the elasticity becomes to what? 1% increase by x1 cause beta percent increase by variable y. So this is what we call the meaning of elasticity. So in terms of measurement units, it's 1% instead of 1 measurement units. 1% of measurement units. Okay? Understand what I'm saying here? Okay, this is, so slope and elasticity is popular in economics because, some of the variables, if we say that in terms of 1 measurement units may be meaningless. For example, if I have the y is the salary, okay, and if I have the x is working experience. So usually we're saying that 1 year's working experience, 1 year's more, or increase by 1 year's, 1 year's working experience will cause by what percentage change in the salary. We don't say that $1 increase or $100 increase, something like this one. We were more concerned with the percentage of the salary increase. So in other words, if 1% change, the meaning of the 1% change is more useful, then we will put the log on the variables. Okay, so with the log, the variable with log, usually we explain it percentage, okay, instead of the measurement units. Okay, so that's the difference. Okay, so if we have the both x and y are log form, then we call them elasticity. An interpretation of the x or y, or in terms of percentage. If either one of the x of y only, take the log. So we call it semi-log. Therefore, look at our semi-log form. We have two semi-log form. One is log x and the other one is log y. Okay, so if we have the log in y, means just take the log in y only instead of the x. There's no log in x. So this is what we call semi-log. And since it is log in y and linear form in x, so usually we say this one is log-lin form. Log-lin means this is log and this is lin. So log-lin forms. Okay? And so on the reverse side is y beta 0 beta 1 log s. Okay? And this is what we call lin log form. And both of them are semi-log form. Okay? But the explanation of the beta 1 and the explanation of beta 2 with log lin or lin log is different. Okay, so for example, how do we explain the beta 1? Since x is in linear form, so we will say that 1 year, for example, I'm just saying that x1 is the working experience, then y is the salary. So we say that increase by 1 year's working experience will cause by beta 1% increase in salary. Okay? But this one, since we put it percentage, okay? So look at the definition. From the table 1, if we have the y is log and x is linear form, then since we explain it as a percentage, so we're using beta 1. We need to times beta with 100. Okay? And if you have this form, lin log form, so we would say that 1% increase by x variables will cause 1%, since it is log of x. So the meaning of that will be the 1% increase in x will cause, since I already put the percentage here, so I have to divide it by beta 1 by 100 to make it as the measurement units of the y. Okay, so understand what I'm saying here? So look at the semi-log. The semi-log form in table 7.1. The third one is using y as a linear form and x is a log form. So the definition of the beta 1 will be if x increases by 1%, then y will change by beta 1 over 100 units. Okay? And if we take the log, natural log of the y, and the linear form of the x, so beta, the explanation changed to be if x increases by 1 units, then y will change by 100 times beta 1%. Okay? Understand what I'm saying here? So this is what we call elasticity here for the double log. And okay, this is the double log. Let's go back to the double log forms. Usually the diagram is something like this one. Okay, and in terms of the beta 1 is between 0 and 1 or less than 0 or greater than 1. The diagram would be different. Okay, how did you call this curve in economics? Anybody knows? We call it isoquant. Well, never mind. Or look at this one. If we have the y is look at beta 1 less than 0. Okay, I think I can take the example. If y is the demand, the quantity, and x is the price. So the demand curve is like this way. So means when the x increases, the y will decrease. The price of the x increase, the demand of the x will be decrease. Yes. Lin log, yes, this one. Well, in the equation, you can have different forms. If I have this beta x1 is like ln, okay, then beta they can have the combination in the equations, not all of them. Since when we explain the beta, individual beta, we will say other variables holding constant, right? So no matter what kind of forms, if I have the equation something like this one, this one, and this is beta 2 x2. Okay, so explanation of the beta 1 and explanation of the beta 2 will be different. The explanation of the beta 1 will be 1% change in x, holding other variables as a constant. Then y will increase by beta 1, 100 times beta 1 measurement units. But if you explain the beta 2 and return to the regular linear form, means that when other variables holding constant, increase measurement units, increase by x will cause by the beta 2 measurement units, increase or decrease. So we can do the combination in the regression equations. But when we explain the coefficient, since we holding other variables a constant, so you just explain the relationship or the form of the x and y only. Okay, it seems pretty popular that we do have the regular y as a y variables and take one of the x as the linear form, a log form, and the rest of the x is also keep as a linear form. It's really it's very popular in economic regression functions. Okay, so we don't really remember what kind of forms of these equations, but we will know that the value of the beta, really will turn out the diagram, the relationship of x, y in different way. Okay, and the typical example for double log functional form, maybe we can take demand law as an example. Okay, all right, and there are some diagrams. Look at this one. This is called semi-log form. And this is using log y, okay, and linear x. And this is linear y with log x. And really, the diagram is different. Okay. Any other examples for this? Well, I think since we are not really studying the economic theory, so we just like to show all of us that when we say the linear regression analysis, the linear means linear in the coefficient, then instead of linear in the variables. Okay, so the diagram you see is not really straight line, or if you have x variables, it doesn't mean that it is a surface. It's a straight surface. Okay, it can be, curve, non-linear relationship. Okay, and okay, we have the examples in our textbook. Okay, say that, look at this one. This is a beef demand. So this is the beef, the consumption of beef. And this is the price. And this is the disposal income. Okay? So this is the regular, linear forms. And it makes more sense that the disposal income is in terms of log form instead of the measurement units. Because when we say that when your disposal income increased by 1% or means more meaningful than increased by $1 or $100, something like this one, right? Okay, so this one will be more suitable, okay, in economics. Therefore, if you change the YD as a log YD, okay, and the result will be a little bit different. Okay, let me ask you. This is the two equations with same y, right? But different x. Although this is log form, this is without log form. Okay, do you remember we learned it in chapter 6 that if you have the information, something like this one, is there any criteria we can use to compare which one is better? This is just the output, right? You can see from this output. So compare equation 2.7 and 7.8. Which model is better? Huh? 7.8. Why? Okay, we can compare just the R square. Okay? Then, if I take the log of the y variable, so for example, if I take the log of the 2.7, the y as a log, and 7.8 as a log, although I really don't have example here, then any criteria to use to compare which model is better. In other words, is adjusted R square a useful criterion? Huh? Yes. Why?
Well, it's useful when you compare two regression analysis model without the implementation of, I would say, non-linear variables, right? because when you logarithm, it's not linear anymore, right? We say that.
Okay.
So maybe even from two different type of analysis, the R square is still relevant.
So you mean
Actually, no. Actually, yeah, if I have to be intellectually honest, I would say that actually it probably doesn't work. Yeah, because there are two different type of equations, right?
so you change your mind?
Yeah, completely.
Okay. Okay. If I have two models with different x variables, I should have the same y variables to be compared with. Okay? If the y variable is different, either the form is different. When I take the log of the y, y variable is already changed the form, right? Okay? So if I have two models with different y variables, either change form or really different y variables, they are not comparable. Do not use any of the criterion which we just say that like AIC, BIC, H, Hanna-Queen's, or even adjusted R square. It doesn't work anymore. So remember that. Remember that. Okay? Those criteria is to be compared, to work with, to perform the comparisons by using the same y variables only. But you can have different x variables, either the original x variable or different functional form of the x variables. Okay? Yes? In x variables? You mean the model is comparable, or the coefficient, or the significance?
Because in this line, you said R squared is not the same as you add
Well, yes, the adjusted R squares becomes from increase from 0.63 into 75%.
R squared is, cannot use.
Yes, we can, because we have the same beta. Yes, we can. So this one is better than this one. And the difference of these two equations is just taking the log of yd only. So they do have different x variables, but this x variables is different functional form. But they have the same y. So in this case, we know that taking the log of the yd is better than use the original x level forms of the x variables.
So we can compare.
Yes, in this case, we can compare.
Right.
But if I'm changing my question that if I take the log of the CB, if I change the CB into the log CB, then they are not comparison. As long as we have the same y, yes, we can compare using those criterion. Okay? So, in the future, if you're working with your thesis, you may bump into the same situation as like I say, right? So which one is better? Then those criterion is the good tool to be used. Okay? All right? All right. Then, okay, the last one is the polynomial form. Okay, look at this one. Okay, look at this one. Okay, I like to say something like this. So this one, I have x1 with 1 is the level form. The other one is square terms, okay? And the other one, x2, is also the level form, okay? So y is equal to beta 0, beta 1, x1 plus beta 2, x1 square, okay, plus beta 3, x2. So I took the derivative of y with respect to the x1. So now I have 2x1, right? So in mathematically, if I take the derivative of x1, then this becomes to beta 1. Then how about this one? Is using this 2 times beta 2, then still have x1. This is math. This is the derivative calculus. Okay? All right? So this is what we say here. Okay? Then, what is this for? Usually, what is this for? Look at the diagram of this one. Okay, this one, this is y equal to, they're just using the same equation as I did here. Okay, and since we are holding x2 as a constant, so we look at the change of the x1. Okay, so if we have beta 1 less than 0 and beta 2 greater than 0, so it means this is negative, this is positive. Okay? If this is negative and this is positive, what do we mean by that? This means that as x1 increases, then it will cause y decrease. Therefore, when x1 increases, then y decreases. Okay? Then, this point, if we make it as a 0, okay? In mathematics, this one, the lower point will be the derivative of the x1 equal to 0. Okay? So in this way, if you have some data, you solve with the beta 1 hat, then you have the beta 2 hat. Then using these expressions, you are able to get what is the x1. And this x1 will be the minimum of the x1, which is the bottom of the x1. Okay? Then after this point, lowest point, okay, then the curve increase. So this means the beta 2 is positive increase. Okay, I think this is easier to understand when we say that we have this polynomial formula, like this one, we call this a parabola. And we have two forms of parabola. One is the U shape. This is what we call U shape. So this is what we also say. The mouth is open, is upward. Then this is inverse U shape. So like this one, and the mouth is downward. Okay, and this one is just the opposite of this one. Okay, look at this one is beta, decrease first, then touch to the lowest one, then turn upward. So beta 2, increase. Then how about this one? Increase first. So beta 1 is greater than 0, increase. Then touch to the point, the top point, okay, then downward. So beta 2, less than 0. So either one of this case, we can calculate the bottom line, the bottom or the top. And usually in economics, this is maybe it's the best quantity produced or the best quantity, manufactured for X1. To solve for this one, this is the most suitable quantity for supply or demand, something like this one. Okay, this is in undergraduate economics. This is important theory. Okay, I'm saying again that if you not really understand the mathematics or the derivative of calculus, really it doesn't matter. Just understand that. Look at the pictures. Okay, then by using the pictures, you see the relationship. Then I think in terms of this way to understand the theory behind, is still workable. So do not worry about, really, you really don't understand the math. It really doesn't matter. Okay? All right, so the polynomial form is also popular. Does anybody tell me the examples in economics? I think in accounting, you learned this one in course accounting, right? Kevin, your major is accounting. You remember that?
Yes.
What is it?
We say
微笑曲线，成本曲线。It's not 微笑曲线。cost function, average cost function. Sometimes we say that, if the company can manufacture some sort of X quantities, and the average cost is when you starting to manufacture some products, the more you manufactured, the average cost is going down, right? Because we have the fixed cost and also the variable cost. And if you produce more, then then fixed cost will reduce. Therefore, the average cost will reduce. But at some certain point, something like this one, this is your maximum quantity to produce some sort of products. Okay, then after that, the cost will increase. Okay, so polynomial form is also pretty useful. Therefore, a polynomial form is also a alternative functional form. In regression analysis, although it is not linear in the variables, but it is really linear in the coefficient. Okay? Any questions about this? Okay, I think we'll really spend some time to talking about the alternative functional forms. Then we do have some exercise for our last assignment, lab number 4, which is in chapter 7. Okay, let's look at this one. Okay, econometric lab number 4. So this is our last assignment. Okay, so it's due on, today is 22nd, right? Is 1 week enough? I haven't finished the chapter. I will finish maybe today. So maybe due on January the 5th. Okay? Due on the January the 5th. Okay? All right. Any questions about the functional form? I just explained it. Any questions?
After the next assignment, we pretty much don't have any graded things, right?
Huh? Excuse me.
After
Sorry.
The next assignment, written assignment,
That's
then it's
the last one.
pretty much finished. After that, I mean, maybe we have to attend class, but there won't be any tests or exams, right?
No test, no exam.
Okay.
In this course, we all turn in these assignments, and totally we have 6 assignments. Okay? I think in this class, the practicing is much more important than the test in the class. Okay? All right? Any questions about this? Okay, if you don't have any questions, let's see. Okay, let's talk about lagged independent variables. 7.3. What do you mean by lagged independent variable? Lagged independent variable. Look at this one. This is what we usually, since we always talk about cross-sectional data, so we never put the T here. Okay, we put it I. Okay, I is usually is for cross-sectional data. But when we say lagged independent variables, we are really in terms of the time. So the notation here, look at this one. If the YT and the X1T, X2T, what do we mean by all this in terms of T? Means in the same period, same year, same month, or same quarter, or, something like this one. Okay? So we say that in some cases, or the authors say in many cases, the time elapsed between the changes in the independent variable and dependent variables. What do we mean by that? Means the T is not T anymore. Maybe the previous X will affect the performance of the current Y. Okay? See what I'm saying here? So if I put an example here. Look at this one. Look at this one. This X1 is T minus 1 instead of T. So in other words, in this relationship with X and Y is using the previous year's X to affect the current Y. Okay? All right? So this example is from our textbook. And usually, in Taiwan too, we have so many situations like, have you heard about that? We have our cabbage overcropped. Have you heard of that in Taiwan? Since the previous years, the price of cabbage is going up. Therefore, a lot of farmers just produce cabbage. Then it affects this year's. Because, all these plants, when they grow, they need to have times to plant and need to have time to grow it. So they have to decide it beforehand. And how many I wanted to produce the following year. And the decision is based on this year's price. Okay? All right? So, in Taiwan, there's in many situations like those fruits or those vegetables, they're overcropped. Then they are expected to have the price something like the last year. But in fact, the price go down. So it affect all the farmers. Something like this one. Therefore, we have the regression like this, and this is called lagged independent variables. Okay, let's take a break.